Hello, this is Marat Kharudinov, and in this video I'm gonna show you how to create so-called invariant datasets for running global SAM using global mode. So first we go to our model directory and go to grids. We need to create grid. So for example, let's create some new grids. There are some pre-computed grids here, but we create, let's create a new grid, say that is about 10 kilometer grid spacing at the equator. So for that we will use number of grid points in a longitudinal direction 3840. This is make sure that this number is actually one of those that allowed by SAM, so they should be divisible by 2, 3, and 5, and you can find the list of those nice numbers at the end of the source domain file, like for example. So at the end you can see, and there is our grid 38. 1920. So this is our nice number. Okay, so first we need to edit the file grid F90. First we need to go to the grid directory. Okay, so here you already put these parameters here, specified the number of grid points in Y direction, number of grid points in X direction. Now our grid will be coarser and coarser towards the pole, starting from some latitude, something like about 64 degrees north-south, and right at the pole it will have grid spacing of in latitudinal direction of 2 degrees, so that the scalar point, the nearest scalar point to the pole, will be at 1 degree. In order to produce grid, you first compile it, try to use optimization 3, because it sometimes creates smaller code that because datasets are large, you may sometimes have difficulty not compiling but running it, because of the memory that you have on your processor. So in our case it should be fine. I'm running on computer that's sufficiently large for that. So okay, now we just execute it. So it will do it magic, and will create grid that will be isotropic in both X and Y directions. That is, grid spacing will be the same at anywhere except for, again, north of certain latitude. So here you see we created a grid, and the last point is at 88.9 degree of latitude, so it's about 89 or about 1 degree away from the pole. Here it also shows resolution in kilometers at that particular point, and this is aspect ratio relative to the resolution at the equator, so it's very, very much coarser than the equator. But as we move to the equator, towards the equator, and reach 64, about 64.5.6, we see that we have actually grid spacing of 4.5 kilometer there, and aspect ratio of the grid, that is delta X over delta Y, or delta latitude over delta longitude in kilometers, it's about 1, so it's isotropic grid. And as we move towards the equator, it will degrade resolution somewhat by about factor of 2. So at the equator itself, which is about here, you see that resolution is going to be 10.4 kilometers in both X and Y, so aspect ratio of 1. Okay, so now we need to copy those files or move those files to give them some name which is going to be permanent, because those will be overwritten next time you use this utility. So move grid, I would say call it lat 30 840 by 9020 divar. Divar means I just use for notation that it's variable grid in y direction. So you see I don't use extension here, same as here. And then we need to copy another file with text extension. So now we have those two files, nice, those two. So now we go to global grids, and here if you don't have anything here, no symbolic links, you need to create new ones. If you do have symbolic links from from a gSAM distribution, I don't know, accidentally left there, just remove them, just delete them. Don't worry, don't be afraid to delete symbolic links, because you don't really delete the directory, you only delete the link. So let's create first the link to a data set that contains terrain and other data. That data set you supposed to download from SAM website, gSAM website. It's called like gSAM global data. So you put it somewhere in storage disk where there is enough storage. And you put, of course, model somewhere where it's like more permanent, that cannot be accidentally erased. So we need to create symbolic link just for short, for convenience, and also all the scripts here actually use those symbolic links. So let's create a symbolic link to that data as ln-s symbolic link creation. This is the name of that data directory, and we call that link data. Also, I created some directories for binary data sets to run the model, and for netcdf data sets that these scripts also may create. So for those I called bnd, and the link should be called bnd because scripts use that. And also ncd, this is for netcdf files. Okay, so now we have links. You see here bnd, data, ncd. Now if we look at data, and you need to use okay, so what we have here, this is in our data directory now, and our bin and nc directories are empty right now. Okay, so now we need to create terrain data set first. Always you create first a terrain data set that so this terrain that in this data set, like a top 01, it's very high resolution terrain, we will interpolate it to our grid using a Fortran program called make2d ter.f90. So here we already specified it here, number of grid points in longitude, in latitude, and also the name of that file that we just created in grids directory, lat, this one with text extension. You don't have to edit anything else here, so only those two things that you need to add. Now you compile it again using O3, because sometimes it makes smaller code, which can be an issue if you run on a computer with small memory. So compile it and then just run it. Okay. So now what we do is create length type dataset. For that we just compile, because that program will now use that particular terrain data that we generated already. Let's see, we'll make 2D length type F90. So you see it will use outer.bin in that we already just generated, and it's actually been written to bin _d directory. So here you don't have to edit anything, or only make sure that your in-out directory is bin d, that's here. So you just compile it. And run. So it will create like 16 length types, and 0 length type is ocean. That will be used by other scripts. But now those files are in binary format. We need to convert them to netcdf, because scripts use those files in netcdf format. So let's convert them by using command ncl. So I forgot to mention that in order to run those scripts, most of them are in ncar command language, and ncl, you need to install ncl on your system. So ncl bin to nc ter. So it will convert this binary terrain file into netcdf file, and the same thing with length type. Okay, so now let's look at ncd. You need to use this slash for that to look at the symbolic links. Okay, so you see we have two netcdf files. Now we need to rename them because they're kind of generic names. Rename them. Let's go in there. We move them. The length type the name should be start with length type, and then use some common name that describes your grid. You will use the same name everywhere in other script, so it should be the same everywhere. So let's use the same that we use for the grid, which is 3840 times or x 20 1920 dy var and C. And the same thing with terrain. Here we use it says ter, but the actual name should always be full name terrain. Terrain, and here we have ter. Okay, so now we have these two nice files. So now let's do the creation of, now we can produce all the binary invariant datasets. For that we use script, ncl script called make. First we should go back. To global data. So make 2D invariant ncl. So here we need to edit basically only one line, which is our grid specifier. Remember that we used to name all our files 3840 by 1220 dy var, and you don't need to edit anything else. If you specify netcdf out, it will also make netcdf files equivalents of these binary files. Mostly they're not going to be used by the model, but they would allow you to check visually using some netcdf viewing software, some interactive tool, if the datasets look okay. But I didn't deliberately make model read directly netcd files, because for many people it's troublesome. Many people can easily produce binary files as input files, but produce netcd files requires certain skill, especially if many time steps are involved. So just to make it simple, the input files are just binary. Okay, so now everything is set, everything is created, so now let's run the script. It will take several minutes, so just hang on, maybe, I don't know, in this case maybe 5 minutes or so, so I will pause my video and then return after it's done. So the script ended. Actually it failed at the end because I misspelled the word terrain, so I changed it, and now when I renamed the file into terrain underscore blah blah blah, I misspelled it, so now it's fine. So now let's see, it should create our files. Let's look at the bin.d directory. So now you see that we have our files. It also contains those temporarily files that were used when we were running our Fortran script, so we can delete them. Let's delete them. Okay, so you see we created 5 invariant files. LAI is leaf area index file, which contains monthly data of leaf area index interpolated to our grid. Land mask, which is just shows where land is, where water is. Land type for various land types, like 16 types. Soil file that contains a percentage of clay and sand in the soil, and terrain file. So we can also, because we asked the model, it created we asked the script, it created actually also equivalent netcd file that you can actually copy somewhere to your desktop or something and look at them using your favorite netcd viewer tool, just to see if everything looks fine. So that's basically it, folks, and thanks for watching, and happy computing.